500 milliliters of air, and that's not important for the first question, but we're going to use it over here. 300 Kelvin, 100 kilopascal. We want to raise the temperature to get the pressure to 120 kilopascal at constant volume. We can rearrange PV equals nRT, putting N, R, and V on the right-hand side. All those will be constant in this case, and conclude that P over T is therefore constant. As a result, we can write P1 over T1 equals P2 over T2, or P1 T2 equals P2 T1, and so forth. One way or another, if we want to get the temperature at this pressure, the bottom line is we can plug into the equations and do it without understanding anything, or we can just understand that the pressure will increase by the same proportion the temperature does. Otherwise, P over T would not remain constant. The ratio of temperatures is 120 over 100, which is 5 over 6, 6 over 5, and the ratio of temperatures is therefore going to have to be 6 over 5, meaning that the temperature T2 has to be 6/5 of 300 or 360 Kelvin. Now, if the volume is 500 milliliters, then and of course that's the volume of air, we can conclude, as we did in previous classes, that the number of moles is 0.02. You can solve PV equals nRT knowing PV, and T for N. And we get approximately 0.02 moles. Not, it's probably off by 10 or 15%, but you get the idea. Okay? CV diatomic, this specific heat at constant volume for diatomic gas is 5/2 R. So that delta Q is going to be the amount of heat it takes to increase the temperature has to be the product of that, which is in joules per mole Kelvin, because R is in joules per mole Kelvin, times the number of moles, which is N, times the number of kelvins, temperature change, which is your delta T. And that comes out approximately 21 joules per mole Kelvin, which is your CV for diatomic, the 5/2 R. 0.02 moles, 60 Kelvin, comes out, I think, about 25 joules.